exam back to you. But after you see your score and whether it's reflect your final exam on Friday or next week, anytime you can come to our office, then we can review exam or my grading again because the questions can be used in the future. So that's the reason I don't see your exam to yourself, right? Okay, that's for exam. So at least today, maybe this afternoon you will get the score. Another thing is about our first group case study. So if you look at syllabus, we have the two group case study. Each one counts for 10%, which is 10 points. And the first case study it will be. I look at the calendar. I was set the date is October 18, which is next Wednesday. So it's 2 weeks, exact 2 weeks from now. Okay, after October break. So I don't want you to rush to before the October break. So you do have time, and also it's not Monday, it's Wednesday. I believe everybody should be back from the October break, right? So it's a group case study, right? I think we have like 20 cases, some students like that. So each group, okay, to have 4 or 5 students. Okay, definitely I ask you preference. So let me know your preference, not your preference, or your group's preference. Say we want to be in the same group by the end of Friday. You have free time to hang out with your friends, right? Know better about each other, right? To see what is a fit. Anyway, so by Friday you have to tell me. So what is your preference? Or just remember that it must be the mutual preference. You can't claim somebody belongs to you without get permission from this person, right? So it's a mutual agreement, and you don't need to have like 4 or 5 people. If you only 2 people, you want to be a group, you tell me. I will try to assign you 2 in the same group, all right? For the rest student, I will divide them randomly to the group. You don't need to worry if you don't really have this preference. You will have a group for that reason, right? Any questions? And then after Friday, when we get the group, and I will assign the case study for each group.
So what exactly do you have to do for the case study?
Okay, so there's a lot of case if you have a textbook. There's a lot of case for each chapter. For example, forecasting. Yeah, it's a little bit tricky than the homework question. I give you some data, analyze that, give you recommendation. So the requirement is that on that particular day, Wednesday, October 18, every group need to come here to do a presentation. So the presentation day, every group, everybody, every member in the group need to come here. And another thing is you have to submit a report, at least 5-page reports, for your case study as a group. So it's not individual work. Right? So it's also good, provide some chance for you guys to practice the written skill. Right? Questions?
So both the presentation and the 5-page paper is due on that day?
That's right.
Okay.
That's right. I mean that's not hard. You have like 4 or 5 students in one group, right?
Yeah, but what about the day after day?
Page of paper out.
And also, I already posted the bonus points for last Thursday's presentation. I will post the bonus points for last Wednesday's presentation. Okay, if you find okay, you find okay, I attend the presentation why I didn't get the bonus, then you let me know. But I will post them today. No questions? Then we can continue our study on chapter 10. Okay, chapter 10. We have discussed the strategy about the inspection. Okay, how frequent the inspection we should do. And also centralized inspection, go to some lab in Chapel Hill, or just on-site inspection. That's a trade-off. Cons and pros for these 2 methods. Next, we'll go to the core contents of this chapter, which is how to build a control chart to monitor our quality. Right. So first, we want to introduce this statistical process control, SPC. Okay. The quality of conformance is a product or service conforms to the specification. That is, the SPC is a tool we can use to help us in this process. It's a statistical evaluation of outputs. So we need to collect a lot of samples to the statistical evaluation. It will be helpful for us to decide whether it's under control or out of control. If it's out of control, we have to take corrective action. For any process, they have variabilities, right? Like us, right? Sometimes we are in the high mode or low mode. We have some variabilities. Two basic questions when we consider variability. The first is issue of process control. Is that random? The variation random? If there's no random variation, the process we should think about as an unstable process. But the process should be, right, pretty stable. Even there's some variation, it should be random variation. Like weather, well, it's really hard to predict. Issue of process capability. And the second variability we should think about. Well, even the process is stable, right? If whether the variability is in a range that satisfy the customer requirements or our criteria. Like I said, okay, my case, well, I think I'm a good driver, but I can't do the parallel parking in downtown New York City, Manhattan. Well, I'm not capable to do that. Okay, this is my variability. It's pretty stable. Right? My parking skill is very stable. But this stable parking skill with a little bit big variability won't make me capable to do the parallel parking in Manhattan. Right? That's two different things. Right? First, what is random or non-random? Second, even it's just random variability, what is satisfy the requirement? This requirement usually can be very high from customer. They only accept very tiny variance of your products or service.
You mean like within the margin of error?
Margin of error? Yeah, it's like this. So think about it. Okay, for example, you go to a bank, you want to get some, like deposit something. Okay, go to bank. Well, some customers think, okay, go to bank, I wait for 0 until 10 minutes. That's my range, right? Most banks can satisfy that requirement in this region. As more 10 minutes, you can some teller will serve you. But for VIP customer, 10 minutes too much. As more 3 minutes. Then you see the problem, right? If that's VIP or high level customer, they only can tolerate 3 minutes at most, and you let him wait for 8 minutes. You can potentially lose this customer. This doesn't mean you have a long random variation for the waiting time. It's pretty random, 0 to 10 minutes, because you only have like 2 people working there. Right? But for VIP, it's different. So probably you have to set a VIP room or maybe hire another person to make sure, okay, satisfy the customer. Clear? Means?
Yeah.
Yeah, that's capability. Capability is related to the variability, but it's not like say whether it's random or non-random. It just say your variance, whether it satisfies the customer, the criteria. Like maybe you say my variance is very stable. For example, my course is always between A and C for so many years. Some course I guess A, some course you get C. Okay, that's no problem. It's very stable every semester. But if you apply like say Harvard, that's unacceptable. They don't want to see any C, even like B- in your transcripts, right? But for you to graduate from UNCP, no problem. Any course above C is a good student. So that's about capability. Variation. Random variation is the natural variation in the output of a process created by constantly minor factors. Well, my understanding for this random variation is that variation we still don't understand for the modulation. You think about it, a lot of variation exists a long time before. There's lots of variation now, like a total eclipse, right? Thousands years ago, when people see the total eclipse, they think, okay, it's a miracle. Okay, it's totally random. It's some god or ghost, and there's a lot of things talking about that. But nowadays, we can predict, we know the exact time of the total eclipse in the next 100, 200 years. We know that for sure. You can prepare now, right? Like 25 years later in North America, that's another total eclipse. So now it's become no random variation. Everybody knows that. Okay, 1,000 years ago, we don't understand. We think it's random variation. But still, we have a lot of things we don't understand, right? We just call it random variation. That's just my personal understanding. Okay, it's a natural variation. Assignable variation. So that's a variation you can identify the reason. Okay, it's a non-random variation. For example, if the first row students they are in the production line from Erica to Kayla, and let's say okay, Kyle is the bottleneck. We have discussed that, right? Why Kyle become the bottleneck? Then we see okay, maybe his working skill is not at the same level as his colleagues. And then it's an assignable variation. It's not a random one. Everybody has a random variation, right, in the production line. But Kyle, his performance is consistently like 50% lower than the other colleagues. And then we can solve this problem by training him, by providing opportunity for him, maybe assign a mentor to him, a lot of things. We can solve this problem to improve his outputs, narrow down his variation. Clear? So that is assignable variation. Sampling and sampling distribution. So if we want to build a control chart, it involves periodically taking samples of process outputs and computing the sample statistics, such as sample means, that's one sample statistics, or the number of occurrence of some outcome, for example, defects, how many defects we have seen. Sample statistics are used to judge whether the process variation is random or not. Control process is sampling and corrective action, only a part of the control process. Those are the steps required to get the effective control. We need to define, okay, what is to be controlled. Right? For example, the bottle of water. What should we control? I think the most important thing probably the quality of the water, the purity of water, and something else. For example, whether the container is easy to broken or not, whether the cap is easy to open or not. So that's something else that you have to control. Right? First, figure out. Okay, even this very simple product, there are several things you have to control. Then measure. Measurements is always important. Remember in chapter 3, before we talk about like 10 different forecast model, the first thing we introduce is measurements. MAD, MSE, MAPE. Okay, how you determine which forecast is the best. Without measurements, even you introduce 20 forecast method, you still can't choose the best one. You don't know how to choose the best one, right? Compare. There must be some standard. You say, okay, you are a very good driver. You have very good skill on parallel parking. It's really depends on standard, right? I'm pretty sure most of you can't do the parallel parking in big city in Europe or China or Japan because that's even tougher than Manhattan, right? But we can't say, if we give the standard in here, in let's say especially in North Carolina, I believe most of you can do the parallel parking anywhere, like downtown Raleigh area, most of you guys, right? Not hard, right? So we need to have this standard. Evaluate, okay, establish definition of the out of control. Okay. If it's out of control, right, we need to discover the cause, why it has non-random variabilities, and fix it, hopefully. Right? And then continuous improvements, keep monitoring whether the problem has been permanently eliminated. That's the steps. So then we'll begin to build our control charts to control our quality. The control charts is a time-ordered plot of sample statistics gotten from an ongoing process. Like every week we collect sample mean, or every hour we collect sample mean for some variable we are interested in. It's used to distinguish between the random or non-random variability, the control chart. You remember the last question, not last question, the last question in chapter 3's homework, question 30. You guys probably will still remember. Last part C said, okay, you build control charts, you plot data to see whether it's random or non-random. Many students get the correct answer. It's under control charts, but it has a cycle. So it's non-random. Right? Then we'll do the same thing here. Right? But we already know a little bit from chapter 3 for the control chart. The control limits is the dividing lines between random and non-random variations. Upper and lower control limits define the range. That's a typical control chart. Right, you can see here. So it's sample numbers like day 1, day 2 until day 12. Right? We build lower control limits and upper control limits. Do you find any problem in these charts, in this plot? Which one has problem? 12. The last data point, right, is out of control charts. Okay. Well, this is not 100% correct out of control because we're talking about this may still under control, even it's out of control charts. But we should dig more. Right? Why is beyond our control charts? We should dig more. Right? Okay, now we'll talk about why I said, okay, so even it's out of control charts, maybe still under control. Okay. That's because the modulator of statistics, you guys like or hate statistics. Anyway, you already finished 2 statistics class, right? Come to this class. So statistics type 1 error. So when we build our control charts and use these charts, right, to monitor whether our performance is under control, and then we find, okay, the mean is too high. You think about it, we can build this shell. You can see that means the height of the shell. Okay, you choose 10 shells every day, and you calculate the average height of shell. And on the 12th days, the average height of these 10 shells you choose too high. You think, okay, there's something wrong with our production line, right? We have the shell average is higher than our control charts. No, so that's out of control. Because there's 2 types of error. Type 1 error. You make the conclusion a process is not in control when it actually is. For example, the last data point here. Well, with the control chart, we think, okay, it's out of control. But still conclusion can be wrong. Why? Why we have this data point on the 12 days, we collect 10 shells we produce in that day. We calculate the average height of the shell. It's out of control. It's beyond control chart. Why Charles still say it can be wrong conclusion? It's still under control. Understand my question? Or question is clear, right? How can it happen? We use control charts, right? You already know the control charts in chapter 3, right? Well, any point beyond control chart, that means something wrong with your production or service, right? Common sense is like that. But that's the purpose of a control chart. But type 1 error means, okay, you draw the conclusion based on your control chart result. You say it's out of control, but in fact, it's still under control. How can it happen? Is it possible? Not possible? You think about how we build the control charts. We build the control charts by our sample statistics. Right? We say how much standard deviation when the control. Remember chapter 3? We'll talk about in a couple of minutes. But it's like, okay, like 3 sigma, 2s, MSE, remember, plus or minus 2s, you build these control charts. Well, the control chart itself, you build that, already have the criteria, you decide. It's 1 standard deviation, 2 standard deviation, 3 standard deviation. If you want to control a big standard deviation, then your control chart is wider. You think about it, right? It's wider. Even you say, okay, our criteria is 2 sigma standard deviation. This doesn't mean this 12 days is wrong. Because we collect, it's a sample. For example, we produce 100 shells every day. We can't collect all 100 shells data because it's time consuming, it's expensive, right? What we do? We collect 10 shells and calculate the average height of this shell, 10 shells, right? That's a sample. You understand the sample, right? Statistics. Sample is a subset of a population. We can do the population, but it's very time consuming, expensive. Most companies will choose to only study this small sample. But so what happens if by whatever reason, the 10 shells you choose at this day is the 10 highest shells produced in that day? Right? If you choose 100 or if you count all 100, that's maybe it's under control. But by whatever reason, lucky or unlucky, You collect these 10 chairs. They show out of control. See the problem here? See the problem here? Let's give another example. You will understand that. Okay, you think about if we are a doctor, okay, we want to monitor the health of the group of students or whatever people, right? We will say, okay, your weight should be between, let's say, 90 pounds, like tiny girl, to, like say, 250 pounds. That's the American's criteria. In China, probably like 200 pounds. Let's say American. So we're 90 pounds to 250 pounds, right? We do have this range. I think everybody here between that, it should be normal, considered normal. But that just say that number. I don't know the exact number. Okay. You think, okay, if somebody is, you see the pounds 280 pounds, you feel it's unhealthy, right? We think, okay, this person definitely is unhealthy because it's 280 pounds. It's out of chart. Okay, remember this is a sample. Okay, you choose 10 people. The average is 280 pounds. You think it's wrong, totally wrong. But you think about, if that's a group of people you choose to calculate their average weight is athletes. For example, NFL players, NBA players. You can't expect Shaquille O'Neal is less than 200 pounds, right? That's his position decide he must be over 200 or even 200, I don't know, 250 pounds, right? So if you choose a group of people, by whatever reason, they can be extremely high, extremely heavy, but they are very healthy. Most of them are much more healthy than us. They are the athletes, professional players. Then we make the wrong conclusion. People don't look back when we see, okay, there's something wrong with this group of people. But nothing wrong. Same thing, heights, right? Like that's a height race. Okay, LeBron James, Shaquille O'Neal, they're out of charts. They're out of charts of this height race. You can't say, okay, Yao Ming, you can't say that they're unhealthy. They're very, very healthy, right? But they just much taller than average people. So that's why we can make the wrong conclusion. If we only study a small sample, I know why we use a sample to plot in the control chart, we make this type 1 error. It has a tiny probability, it's not common. Type 2 error, similar thing. We make the conclusion that it's under control, but it is not. Same thing here happen. Any point is under control, maybe we're just lucky to choose a subset they're under control. If we study the whole population, maybe like the 11 state, it's already out of control. But because we choose a subset, these subsets may be very different with the whole population. You see the problem here, right? For example, if we want to study UNCP students, we have more than 6,000 students, right? And then we say, let's study management's 4410, this section, face-to-face section. Well, you guys are fantastic students. Even I have not graded your middle-term exam, but let's assume you guys are fantastic students, right? And then whatever we get from this group, like every GPA, whether it's healthy or not, good shape or psychology status, we get very good results. And then we use this result to make a conclusion for UNCP students. We say everything is under control. This can be biased, right? Because we only study these special subsets of all UNCP students. So type 1 and type 2 error. Clear? For these two errors, why it happened? It's clear? Subsets creates problem. Okay, now the question is, why not just direct study population? Why collect all the data? Why not don't choose just a sample? We collect all the data, study it, then we won't make any type 1 or type 2 error because we know everything about it we produce. Dylan?
Very time consuming and costly.
Yes. And sometimes it's impossible. Even as, for example, US. Well, we do have like population census every like 5 or 10 years. But even that, we do that. Anybody lock your door? Nobody lock my door to say, okay, how many people you have in house. I think they still do the sample, right? They lock some doors. But not every house will count, right? So even when we do the population count, we say we have like 310 million people in the United States. Well, that's still a roughly estimation. The exact number, we never know. We don't know. Well, there's no way you know that, right? Any country, except maybe a tiny country, but any country, more than like 10 million people, you never know exact number of people live in that country or citizen, even citizen of that country. You never know, right? Okay. Type 1 error because like LeBron James, right? Kobe Bryant, they are in this upper tail, right? And then when we study this group, we say, oh, there's something wrong with this group. Nothing wrong. They're just in upper tail. Similar, some people or some products, they were following the lower tail. Nothing wrong. But when you build a control chart, right? You can't say, okay, from negative infinite to positive infinite. There is no points to use control chart. You have your standard, like 2 sigma, right? Mean plus minus 2 sigma. So that's your control chart. Then you know that, okay, you can make the wrong conclusion with a tiny probability. It's out of control, seems out of control, but in fact, it's just the modulator of this normal distribution. People, service, products, we all follow this normal distribution. Upper tail and lower tail. It's clear? That's why we have type 1 error. Observations from the sample distribution. For example, that is our distribution of our process, like products. So every day or every week, we collect the sample mean, okay, collect some products, like calculate sample mean. Here in this graph, it shows under control. Okay, for the control chart, there are different types of control charts. First, we'll introduce the variable control chart. So variable generate data that's measured. So like continuous data, right? People's weights, heights from the baby boy is like 3 or 4 pounds. The baby until I heard that that's one lady just passed away. I heard the news. Her weight is like the peak time. Her weight is like 1,000 pounds. Well, that's probably the world record. But that exists, right? That's a continuous exists from 4 pounds baby boy until 1,000 pounds. That's our human, right? So that's measurable. Any number between that range is possible, right? It's possible. Then we build this mean control charts, use this mean control chart to monitor the central tendency of a process. It's also called X-bar chart. X-bar, do you know what is X-bar?
That means mean, right?
Yes, means you're very smart, right? X-bar, right? So that means the mean, right? Ranging charts, we'll talk about ranging charts, is used to monitor the process dispersion. Okay, we'll talk about that too. It's called R charts. First, before we build the control charts, whether it's mean charts or range charts, we have to calculate some parameters. First one is the grand mean, X double bar. The grand mean is calculated in that way. It's summation I from 1 to k xi divided by k. Okay, so let's explain what does this mean. From I to 1 to k xi bar divided by k. Okay, let's say we want to study the academic performance of students in UNC Pembroke, right? We want to study that and say what is the average GPA. Nowadays, it's pretty easy. We have a database. It's easy to calculate average GPA. But let's say 15 years ago, we don't have the computer or have all the record here. We do have the paper transcripts for each student. Then what we did is collect a sample. Like for example, we go to Charles' class. Let's say we collect 28 students in this session and calculate you guys' average GPA, right? So it's 28 students, right? We calculate X1 bar, 28 the average GPA in this session. That's the first data point. Clear? It's a sample mean, 28 students. And later, we go to Dr. Doyle's class. And we collect another sample. I don't know how many samples they have, like maybe 28 again. You calculate that session's average GPA, X2 bar. We do that for like 10 sessions, 10 classes. And then, how do you calculate X grand mean, X double bar? It's pretty simple. We have these 10 sample means, we add them together, divided by 10. That's the grand average. It's clear? How do you calculate X double bar? Questions? Clear? Everybody? Clear? How do you calculate X double bar?
Wait, so you would add up all like the 28s basically, or say it was like 20?
Well, 28 is just a sample size. It's not in this formula. So this only affects you when you calculate the X1 bar. Because when you calculate X1 bar, how you calculate? If you have 28 data, you add them together, divide by 28. That's how you guess the X1 bar, X2 bar. Right? Once you guess X1 bar, X2 bar, you just sum them together. This K is not a sample size. is how many sample you have. So k is equal to 10 in this case. K has nothing to do with 28 or some number. 28 is your sample size. It can be confusion. We have example. I would expect students also get confused when you guys are doing the example. But yeah. So R bar is pretty easy to understand. R bar is summation I from 1 to k Ri divided by k. Okay. So that means each sample we calculate the range. For example, this group of students, you guys, 28 students who has the highest average GPA, who has lowest average GPA, then we get the difference. That's the range. After we get these two parameters, we can go ahead to build the control chart for mean X bar chart. So X bar chart is widely used. We want to monitor our area performance, right? You think about it, when we do care of students, but when we talk about students, we don't talk about individuals. We say the students in school business, what their performance. Students in the UNC Pembroke, what their performance. Students in all the UNC system, what is their area performance. That's what we're talking about. That's why X bar chart is so useful. And to build X bar control charts, we need to calculate the upper control limits and the lower control limits. Upper control limit is X double bar plus Z times sigma X bar. The lower control limit is X double bar minus Z sigma X bar. Well, sigma X bar is the standard deviation of distribution of sample means. As is hard to remember what's the definition, but you just remember this formula. So sigma X bar is equal to the sigma, which is the standard deviation of the process. Okay, it's given. Divided by divided by the sample size, which is for example in this class is 28. Divided by sample size n, and you get minus 1. This case is the case that we know the standard deviation process. If we don't know the standard deviation process, that's another formula we can use to build control charts. Okay, is X double bar plus or minus, it's plus minus, plus minus A2 times R bar. Then we can build this control chart. Well, A2 is a control chart factor based on your sample size. That's A2. So if you have a textbook, you can find this chart or table in your textbook. So you can see that here. Give me the sample size, for example, sample size, let's say 10. Right? Then we can find A2 is 0.31. That's how we get A2. So your textbook, the chart is already there. Right? But you can search these charts online, in Google, everywhere. So we use this A2 if we don't know the standard deviation. If we don't know sigma, then we can't use the first formula. Because if we don't know the sigma, we can't calculate sigma X bar, we can't build a control chart. Then we can go ahead, just plug in A2 and also calculate R bar here to build our mean control charts. The ranging control charts, that's more straightforward. So upper control limit is D4 R bar, and lower control limit is D3 R bar. Okay. And here, in this table, is also given D3 and D4, given the sample size. The textbook table is also here. Okay. Before we go to the example, let's talk about our ranging charts. Right? Well, I think it's pretty straightforward why we use the mean control chart. Because we want to control the average performance of our product, of our service, of our people. Right? We want to calculate average. Everybody talk about average. We're not so interested on special case. But why we also need to control the range? The range control chart is used to control the range. You see, okay, the range should be from 0 to 2. If it's about 2, then we think something wrong. Why the range chart is useful for the quality control? My question clear? Range chart, right? When you talk about like people, you think about okay, average performance, like UNCP. Why you come to UNCP? Right? You can see, okay, every student performance. Okay, people's general feeling about university. Okay, whether it's generally safety or not, definitely that crime happen every year, right? So you look at this average statistics and you decide, okay, I want to go to UNCP. So it's like our decision most time is based on the average performance. So we understand mean charts is very useful to see the average what is happening. But why the range matters? Some companies they still care about the range.
Well, the range is kind of like the middle of the all the numbers, you know.
Mm-hmm.
So
Yeah, the range is the maximum minus minimum, right? It's maximum minus minimum. Dylan?
Because the range is good in defining how close you are together, almost like quality control. Is everything that's coming out the same, or is it one's really low and one's really high?
Yeah, I think Dylan make the point that when we talk about mean control charts, we talk about average. We didn't tell the dispersion or fluctuation of this group, right, products. Well, some customers maybe don't care too much, or some industry, okay, means the most important thing. They can accept a wide range, right? But some groups are not. For example, let's say the cars, right? You guys got cars. Let's say the Ford and GM, they have two sedans. Okay, their miles per gallon is the same average. It's the same. Right? When we consider miles per gallon, we didn't see any difference for the average. But the Ford's car, okay, that is every car you bought, the miles per gallon is in this rate, 29 to 31, average 30. GM, 25 to 35, average is still 30 miles per gallon. Then, do you have a preference now, given the range? Which one you probably want to go? Ford or GM?
Ford.
Ford, why?
It's more predictable.
Yes, more predictable, right? Customer, right? Many customers, when we choose buy a car, we want a stable car. We don't expect, so we pay the money for the Taurus, we get the Ferrari quality. That's not our expectation, right? But we want stable. Okay, we don't mind, we get only 31. That's fine. Well, I'm not so jealous of some people buy the GM get 35 miles per gallon. But it has a big concern if it gets 25, right? 25 miles per gallon when you are the advertisement says 30 average. So you can see this also define our quality. Same thing here. You go to a fast food restaurant, right? McDonald's, let's say KFC. Well, the average wait time is they're all 3 minutes, but McDonald's from 1 to 5 minutes every 3. A KFC can last to 10 minutes, even average still 3 minutes. Then, during the lunch hour, okay, probably we'll go to McDonald's because we know maximum is 5 minutes. But KFC, you never know. It can last for like 10 minutes, right? We can't afford. So that's the reason. Beside the main control charts, we have also considered range control charts. Okay, that's the reason. It's clear for this reason? Questions? No? Okay, so we have talked about a lot of the control charts. Well, I just want you guys to remember that, again, you can't 100% rely on the control chart. That's very important. We teach math, we teach quantitative stuff, but we can't 100% rely on quantitative stuff. Like Charles, I do math probably for the whole life, but I can't rely 100% on the math. I do that. The reason is clear, right? We're talking about statistics. Well, if you can calculate every single data point in the population, okay, more than 300 million people in the United States, you know everybody, you know everybody's data. Okay, no problem. You know everything. Then we have no doubts any results you make the conclusion, right? But the problem is that we can't know everybody of these 300 million people. We can't know everybody in this 6,000 population UNC Pembroke. Then we have to study some sample. We have to. It saves some time, it saves our cost, but it has one fundamental drawback is that it's statistic. It's just a small subset for the whole population. So when we study that, we always need to keep that in mind. Okay, especially when we find a problem. You're so excited, say we find a problem, we have to work hard to solve this problem. But maybe there's nothing wrong. You have to look again to see that. For example, one day you collect a sample, you find, okay, in McDonald's, why today average wait time is from 3 to 5 minutes? Something wrong with our procedure. Maybe just that day is like football day, right? That's everybody come to McDonald's, right? And then after football days, everything goes back to normal. You want to keep that in mind. Don't just look at the number. Look at when it's out of control. If it's out of control, you should dig deeper. That's correct. But prepare. Even you dig deeper, there's nothing wrong. You should be happy about that. If you dig deeper, there's nothing wrong. Because you know that, oh, that's maybe type 1 error. Same thing here, type 2 error, which is harder. Well, you pull the control chart, you find nothing wrong. There's still something wrong. Right? Because you luckily, every day you collect a sample is the best employee's products. And then for this small sample, everything is good. But you should also keep that in mind by your observation. There may be something wrong in your facility. And for the sample size, I think Dr. Richard or Dr. Victor, they have teach you guys. Okay, sample size is very important to choose a random sample, right? Not just collect all, like say the students like about 30 years old. That's a bios sample, right? You have to choose a student group that is random. Okay, different race, different background, different hometown. Okay, different gender for sure. So that's sample size should be random. But even with a random sample size, again, right, it's a sample. It's very hard to control the sample. We want the sample to be very similar to the whole population, but it's impossible because it's a sample, it's a subset. So let's keep that in mind. When you see the sample is out of control, dig hard, find where is really problem. If there's problem, take some corrective action. If there's no problem, move on. Same thing here. Even you find the control chart is under control, it doesn't mean you can sleep stably 10 hours in the evening. You should think about, okay, anything we miss from the data. Clear? That's the basic idea of quality control. That's the end of today's class. We'll see you guys on Friday. Remember, on Friday, you have to tell me who is your friend.